Okay, welcome everyone. So today it's a pleasure to have Deepanshu Vasal here. He's, although it says University of Texas Austin, he's actually going to go to Northwestern University very soon. He got his PhD from University of Michigan, Ann Arbor. So today he's going to speak about decentralized decision making in the presence of strategic users.
All right. Thank you, Professor Sundaresan, for hosting me here, and thanks everyone for coming. Today I'm going to talk about strategic decision making when people have different information. To motivate my talk, I'm going to start with some examples, some relevant examples these days. One of the important applications that is upcoming is cyber physical system or Internet of Things. And the basic idea is as follows, that there will be like multiple sensors and controllers, suppose in a room, and they will sense some data. For example, if you are present in the room, what is the temperature, what is the humidity, and so on. And based on this information that they receive or they sense, they're going to make some decisions whether they want to turn on the lights or whether they should turn on the refrigerator and so on. So there are a lot of these sensors that are integrated together through a network. They have some different information that they receive privately, maybe some public information, and they have to make a decision jointly in order to maximize some performance criteria. This information that they receive can be dynamically evolving. And the question that we want to ask is, how can we analyze such systems? What are the best strategies for these players? When should they communicate? When should they sleep? What are optimal policies for these agents that maximizes certain performance criteria? So that is one upcoming applications where we have these different agents, multiple agents who have different information, and there's a dynamically evolving data underlying. Another important application is smart grid. So in smart grid, there are multiple power producers. For example, you can have a wind power plant where at plant you have a wind energy, that is a private information of the wind producer, how much wind do they have in a particular day. And this wind could be evolving in a Markovian fashion over days and over months. There is solar power plant, which again have some amount of sun that they receive, and different kind of power generation techniques. And on the other hand, we have like different consumers. For example, we have home where people are going to use this electricity at a dynamic price, and the kind of decisions that they have to make is when should they turn on a particular appliance so that it minimizes their price and also maximizes some sort of utility. So they don't want to accrue a lot of discomfort because of using these appliances that late at night or something like that. So all these there are different decision makers who have so many different information, and they are interacting together. This information is again dynamically evolving. So again, this is a classic example where of multiple agent decision making, where people have different information, and our goal is again to design some such efficient systems where these users are using some sort of optimum policies to maximize performance criteria. Another application that I want to talk about is cloud computing. So in cloud computing, the idea is that you as a user, maybe as people or maybe as firms, they have certain project that they want to compute certain data, and they will give this data and the computation to a cloud, and there are a lot of servers. And at the server level, you have to make a decision to where to process this data, at what server. So they have their own private information as to how much capacity they have, how many people they have received the request from. And on the user side, you have your own private information as to how much you value this processing, like how much data you have and how much are you willing to spend to process this data. So again, there is this interaction of multiple players with different information. And again, the question is, what is the right way for us to analyze such systems? These are just three upcoming applications, but in general, there are a bunch of different problems where one can think of having similar ingredients. For example, in communication networks, sensor networks, queuing systems, markets, either energy or financial markets, Social networks, for example, like as people, like, we have our own beliefs about a product, like our own private information, and we observe everybody, actions of everybody else, and we want to ask the question, how can we describe our behavior? Well, so there are some interesting phenomena such as herding behavior that have been characterized using such a system. So there is a list of unending applications where we see this kind of multi-agent decision making. And the question I want to ask in this talk is, how can we, do we even have a conceptual framework to understand these kind of problems? So I'll start with what are the basic ingredients in the problem so far. We have multiple agents, and these decision makers or these agents can either be cooperative, and by cooperative I mean that they have the same goal. For example, in a room, these sensors in a cyber physical system may want to maximize your comfort level at the minimum price. Or they could be strategic. For example, in a smart grid, the producer have their own goals. They want to minimize their cost of production, whereas a consumer, you want to minimize the price you want to pay and maximize your comfort. So these agents could have different or the same goals, and when they have the same goal, I call them cooperative. Otherwise, when they have different goals, I call them strategic. They have an objective where they want to maximize an expected either social reward, which means the reward of everybody else, everybody together, or self-reward, which means that when they're strategic, they want to maximize their own expected total reward. There is an underlying dynamical state of the system that is evolving, and we model it in a controlled Markov process. And this information is not perfectly observed by everybody else. So everybody is making some information, asymmetric information, which is not commonly available to everybody. And they take these actions that partially affect these evolution of the state. And our goal as a designer, as engineers, is to either characterize optimal or the equilibrium behavior of such agents. Okay, so this is the problem statement that I want to address in this talk. In order to go to this multi-agent system, I want to start with what do we know about single-agent systems? How can we optimize that problem? So I want to start with a very simple problem. Suppose there's an apple seller, like, next to your house, and she has an XT stock of apples on day T. She makes a decision to buy UT amount of apples on that day, and at that day she gets a random demand of people who want to buy that apple, and let's say that demand is WT. So on day T plus 1, you can see the amount of apples she has on day T plus 1. XT plus 1 is the amount she had on day T plus whatever she bought minus the demand, random demand, and this is always a positive quantitative, so there's a plus over there. So this is the dynamics of the stock of the apples she has every day. So in general, she observes the amount of apples she has on day T. So the information available to her on day T is x1 to xt, the amount of apples she had on day 1 till day T. And in general, her decision of buying the number of apples on day T could depend on this information. So it could be any, this UT could be any function of x1 to xt in general. She gets a reward on day T. Let's say this reward is a function of xt and ut. For example, this reward could be that if you're buying too many apples, if UT is too high, then a lot of the apples could rot away. So you don't want to buy too many apples. Also, you don't want to buy too less number of apples so that you're not meeting the demand. So you are cutting on your profit. So somehow you want to buy enough apples that meets the demand, almost meet the demand in a statistical way. And her objective is to maximize the total expected reward she gets till day T. Okay. So it seems like a very simple problem. Suppose, like, this is one of the premier institutes in India. So suppose she comes to you and asks you, how should she design her strategies? How should she take her action so that she maximizes her total expected reward? And she says that you are one of the premier, one of these people in the premier institute. Can you help her design these strategies? Let's see how difficult this problem is. So in general, as I said, the action ut is of an arbitrary function from x1 to xt. And at day capital T, the last day, there are cardinality of u to the cardinality of x to the times capital T possible number of strategies for her. So which means that the complexity of this problem is double exponential in time t. The complexity at time capital T dominates the whole complexity of all the days, and this complexity is this complexity. I can actually show you why that is the case. So if I have this ut, which is a function of gt from x1 to xt on day t, so the total number of possible strategies are cardinality of u times cardinality of this, which is u x t, and at day capital T it dominates the whole complexity. So that's why the complexity of this problem increases double exponential in time. So even if I take, like, for example, u is binary and x is binary, a very trivial example, and let's say day is equal to 5, the total number of computations you have to do to find the optimum policy is 4 billion, and that's astronomically huge. And this grows double exponentially. So for any reasonable amount of time, you can't even hope to solve this problem. And that's how difficult dynamic optimization problems are. But there is hope. If we know that there's more structure to the problem, if we know, for example, that these demands WTs are IID, then we know that there exists an optimum policy that can be found using what is called dynamic programming, which reduces this complexity from double exponential in capital T to linear in capital T. And that's phenomenal. And the way this dynamic programming methodology works is that you first define a reward to go function for this player. At time capital T plus 1, you equate it to 0. And in a backward recursive way, you find the optimum policies as follows. So for time t, capital T, and so on, you find your optimum action that maximizes your current reward and your expected reward to go. This optimum action is found for every x, and then you plug in this optimum action back into this equation to find the reward to go at time t. So in a backward recursive way, you generate these optimum action ut star and reward to go vt, and the complexity of this problem is basically linear in time. So you have reduced the complexity of the problem from double exponential to linear, given that you have more structure in the problem, which is the IID nature of the noise, or equivalently, there's the state has a control Markov structure. And this idea has been used, like, since 56. This has been used in many different applications. For example, in Viterbi decoding, in communications, resource allocation problems, shortest path. The list, there's like pretty much any dynamic optimization problem you will ever deal with, most likely you are going to deal with dynamic programming. There's no other way for us to even think about solving such problems. So that's how powerful this idea of sequential decomposition is in dynamic optimization problem. Okay? So this is what we know for a single agent problem when we have Markov structure. And now I want to go to, like, what happens when we have multiple players. So multiple players, multiple agent problems, there are, yes?
One question in the previous slide. Your actions depend on all the states that you've observed so far, right?
Could potentially depend on, yes.
In MDP, you don't have access to the previous actions, right? You're doing it in backward.
Yes.
So how do you define the maximum? Do you over there?
This you act.
Line. Yeah.
I'm sorry, I didn't understand the question.
The action in equation 2.
Yes.
The use that you can select depending on what you've chosen in the past.
Yes.
Right. But
so here UT only depends on my current state xt. It doesn't depend on the past. Okay, so there are Markov policies. Any other questions? Okay. So there are two new dimensions in the multi-agent problems that come about that are not there in the single agent problem. First, that these multiple agents could have different objectives. Single agent problem doesn't have that problem. So if they have the same objective, I call them teams, which means that they are cooperative. Or if they have multiple objectives, we call them games. This is this dimension. And the other dimension is about the information. Single agent agent problem with perfect recall always have what is called symmetric information. But these multiple agents can have different information. So there is this different dimension of symmetric versus asymmetric information and team versus games. So let's see, what do we know about, how do we have a conceptual framework to solve such problems in these dimensions. So if agents are in teams, which means that they have the same objective and they have the same information, this is equivalent to saying there's a single agent problem. So equivalently, you can use all the machinery that is known so far for the single agent problem, basically the MDP and the POMDP theory, to solve such kind of problems. So we know how to tackle such problems conceptually when they are in this domain. When the users have symmetric information and they are strategic, again we have notion of equilibria, subgame perfect equilibria, and Markov perfect equilibria. And again we know there's a backward recursive way to find these equilibria. So we know a methodology to compute such equilibria. Things get a little interesting when we have teams and the people and the players have asymmetric information. And not too long ago, there was a formalization of so many techniques available in the literature. And there was this common information approach that came up, which gives a dynamic programming like methodology to compute optimum policies. And I'm going to talk about this in a little bit. Now, what happens if the users are strategic and the information is asymmetric? There's a notion of equilibria in these cases, which is called perfect Bayesian equilibria, sequential equilibria, trembling hand equilibria, and so on. And until 2015, there was no methodology to compute such equilibria. And this is going to be the focus of my talk. How can I give a conceptual framework to compute these equilibria? I'm going to talk about why this problem is hard. So let me go to dynamic games. So I don't know how many people are familiar with what are dynamic games, but dynamic games you can think of, there are these players, strategic players who are observing some random variables and taking some actions. And I can represent this process through what is called an extensive form, which means that I represent it on a tree, where each node in the tree represents all the random variables that have been realized so far. So for example, if I'm at this node, these random variables have been realized. Now I'm going to talk about dynamic games of incomplete or asymmetric information, which means that if I'm player I, and if I'm at some history, I don't exactly know which history I'm at, because I don't observe all the random variables. All I can say is that I am in some information set. Maybe I'm at this node or maybe I'm at that node. That's all I can say. Now I want to compute, so in this kind of games there are, the notion of equilibria consists of two things. One is called a strategy profile for all the players, which I call beta star, which is basically a map from every information set of a player to its probabilistic actions. And there's another thing called belief profile, which means that for every information set, a player puts a belief on exactly which node which it is at in that information set. So for example, for this graph, if I'm player I and I know if I'm at this history, I don't know exactly where I am because I don't perfectly observe it. I put a belief, maybe with probability 0.2 I'm at this node, and with probability 0.8 I'm at that node. So I need to define some sort of equilibrium beliefs on my information set at where I am at in this game. And based on this equilibrium belief, I'm going to find my equilibrium strategies from this game for the game below this. So the equilibrium strategies will be optimum or in equilibrium with respect to this equilibrium belief, the belief that I'm going to use at these nodes. So my equilibrium strategies beta star depend on the equilibrium beliefs I use at this node. But equilibrium beliefs here depend on the equilibrium strategies of all the players before this game. So, and they have to be consistent using Bayes rule. So the equilibrium beliefs depend on equilibrium strategies beta star using Bayes rule. So there's a coupling argument between beta star and mu star. The beta star is optimum given mu star, and the mu star depends on beta star using Bayes rule. And one can think of this, there's a huge fixed point equation in beta star and mu star for this whole game, for all the players, for all the histories of the game, and all the information sets of the players. And this, the complexity of this fixed point equation grows double exponential in time. In a similar way, the complexity of the dynamic optimization problem in a single agent problem grew double exponential in time for optimization problem. And that's the basic problem that we want to attack here. Is there a way for us to break down this big fixed point equation into smaller fixed point equations that are linear in time? And that's what I'm going to talk about. Okay. Any questions so far?
Can you say what you? I didn't understand the last sentence that you said.
So what I said is that this there's this coupling of beta star and mu star, and these the space of these beta star and mu star is for all histories. So the complexity of this fixed point equation is grows double exponential in time, And that's why they are as intractable as the dynamic optimization problem was if I did not have the dynamic programming. Now the question that I'm going to ask in this talk is there a way for me to decompose this fixed point equation into smaller fixed point equations so that I can reduce the complexity of solving this fixed point equation from double exponential in time to linear in time?
You are also going to do this at every stage?
Yes.
In the sense that this is the analog of the perfect
It is.
Bayesian equilibrium.
Yes. It's not an analog of Bayesian equilibrium. If you're there.
No, but there are beliefs here.
Right, but there is similarity, but there's a crucial difference. I'll talk about it when I talk about my algorithm. Okay, so this is my model. There's a discrete time system, a dynamical system, n strategic players over time horizon t. Player I privately observes this type xit, and these types evolve as a control marker process where they only depend on the previous type of all the players and the actions of all the players, and they're conditionally independent across players. So this is xt is basically this vector, and I can write this probability as a product of the individual kernels.
So you are saying that my own dynamic doesn't impact the dynamic of the other?
Yes.
But
Well, they do through the actions.
So action is correlated among players,
Yes.
but I have my own dynamic.
Conditional on action, they're independent. Yes. Okay. So in this case, there is information asymmetry. The users observe actions of everybody else, but they only observe their own private information. So this is the asymmetry of information. So their action AIT is a function of AI1 to t minus 1 and xi1 to t. Every user gets a reward Ri, which is a function of xt and at, where both of these are vectors. Whenever I don't include anything on the superscript, it means that I'm using the whole vector of all the players.
Strategy space here is finite.
This is a finite game, so yes, the strategy space is finite, but it does increase double exponential in time. And the objective is to maximize player I's total expected reward over time. Any questions on the model? No? All right.
So once again, you have defined what about the actions of others?
So every player plays actions, which is an arbitrary function of the information
It's
set.
given, is it? Okay.
So I have to design these equilibrium strategies.
So you're defining an equilibrium here.
I am defining my model here. So this is the model. This is how they can play an action, which could be an arbitrary function of the information that they have.
No, but when you take that expectation,
Yes.
you also have to take into account strategies of others.
Right. So this G
Means
means
what?
for all players I and for all time t.
So the player fixes all the other players' strategies as G sub minus I.
So this is not the definition of the equilibrium. I'll talk about it.
No, I want to know what the G is when you're optimizing over GI. The others are fixed, right?
Right. So for any GI fix, I want to maximize my own G. When every G minus I fix, I want to maximize GI. Okay. So I want to take a step back. This is the game model. I want to take a step back and ask myself the question: how would I solve it if this were a team? What do we know from the team problem when users are cooperative? So in the decentralized team problems, suppose the information structure is the same, which means that the asymmetry of information is the same. But suppose that they want to maximize a common objective, let's say R of xt and at, where we say R is like the sum of everyone's reward. So this is a cooperative team problem. And the problem to be addressed here is that there is a common information A1 to t minus 1, and there's a private information xi1 to t for the agents. So this is not a traditional MDP or POMDP problem. This is what is called non-classical information structure. And the main fundamental problem is that the domain of the policies increase with time. So the domain of this increases exponentially in time, and that's why the number of strategies grow double exponentially in time.
But this is because you decided, right? You could have defined a GTI depending on AT and XT, right?
But I don't know if that is optimal.
You don't know also this if it's optimal.
But this is the best I can do. This is all the information I have.
Right? And so since when in game theory more information imply a
I'm
better
not talking about
equilibrium?
games right now, it's a team problem.
And it has been proved that in team problem, more information will always bring more.
So think of it as the following. If I have an optimization problem, if I'm optimizing over a bigger set, the optimum solution will always...
Yeah, but because of, I know what you are saying, but because of the problem of infrastructure, information structure and so on. So at least for me, it's not trivial how to prove it. For,
Again, the proof is, so let me rephrase.
This is a team problem.
In an optimization problem, it is always true that more information is potentially better. And the proof is that you are maximizing over a bigger set.
I mean, a related question is you're also restricting to deterministic policies.
No, I'm not. These are probabilistic.
G dot is a probabilistic.
So it's like a measure on the actions. So actions are probabilistically taken with respect to these.
Okay. So then there is another question which could be on trajectories. You have probabilities on trajectories. This is for given a fixed history, you're looking at one action being random, but you could also randomize across trajectories.
What do you mean by that?
Oh, wait.
Do you mean like behavior strategies?
No, this is a behavioral strategy. But I'm just saying that paths could be random, rather than just one sample could be random. So it's okay to restrict attention to this, but is there some justification to say that this suffices?
So I'm just I don't understand what is an alternative.
The alternative is you randomize across paths rather than just randomizing based on the history for just the next sample.
I think
Maybe we can take that.
I think in the game theory of Osborne and Rubinstein, they argue that in the games they're equivalent. That you can if you can find an equilibrium, so you can find a strategy which you define randomizes for the whole trajectory. It's good enough to restrict yourself to this kind of strategies. But yeah, in team problem, I can only restrict myself to deterministic. I don't even have to go to probabilistic. Okay, so the problem that I want to attack here is that I don't like this domain of strategies increasing with time. I want a sufficient statistics, something that the domain of which doesn't increase with time. So I want to find some sort of Markovian strategies that are optimal. So there are two ideas from the literature that I'm going to use for that. The first idea is what is called agent by agent approach by Ho in a paper in 1980s, and it argues that given the Markov structure that we have in this problem, there exists optimum policies of the player I that only depends on xit. It doesn't depend on xi1 to t-1. So user I can discard its private information history, and the argument goes as follows. It says that so there are these multiple players. Suppose all the other players other than user I play any arbitrary strategy G minus I, which could depend on anything. Then the user I faces an MDP with the state A1 to T minus 1 and XIT. And thus by the standard MDP arguments, there exists an optimum policy that is a function of the current state, Markovian policy. And that's why you can discard all the private information history of player I. And since player I is arbitrary, you can do it for every player, and every player has an optimum policy that is a function of only its current private information. Okay. Any questions? So this is one level of simplification where we have reduced the domain from xi1 to t to just xit, and that's not very surprising. It's like standard Markov process tools. Now I want to compress this action history into something that doesn't grow over time. So I look at each agent's action AIT, which is a function. So in general, AIT is a function of this growing action history and XIT. And I can think of this strategy as a following two-stage process. I can first assume, so suppose for simplicity, suppose there are two players and player 1 observes xi and player 2 observes x1 and x2. These are their private information. We suppose that there is a fictitious common agent that observes this common information A1 to T minus 1, and it gives a prescription functions to the two players, player 1 and player 2, we give prescription functions gamma 1 and gamma 2. So this gamma I is a function of psi I t of this common information, and these agents basically just implement these prescription functions on their private information to generate their actions AIT. So equivalently, I can say that these AITs are generated by implementing this gamma IT on their private information, which this gamma IT was generated by this common agent by operating a policy psi IT on its information A1 to D-1. So this is basically an equivalent way of saying that I had this bivariate function GI and I'm writing it as two univariate functions. It's a very, you can say that this is a trivial way of writing this policies. And there's a one-to-one correspondence. So any policy G, I can implement it in a psi form, and any policy psi, I can implement it in a G form. But this new way of looking at this policy generation has importance. Is it clear how we what we are doing? So again, just to summarize, we are assuming that there's a common agent that observes this common information, generates these gamma functions, which are now actions of this common agent, and these players basically just implement these gammas on their private information to take the action. So now the whole control process is with this fictitious common agent that observes the common information.
And this common agent will have some goal, right? I mean,
So the goal of the common agent is the common goal to maximize the total expected reward.
Okay,
So it's a team problem, right? So, and the thing is that it's a fictitious common agent, it observes this, it can form this policy, but since both of these players observe this common information in a decentralized way, they can implement this common information locally, common agent locally. So I can view this decentralized problem as a centralized problem of this common agent. So that is a new idea of Nayyar, Mahajan and Teniketsis in 2013. So I can think of this this problem as a POMDP problem for this common agent. So basically I've transformed this decentralized problem into a centralized problem of a common agent, where this common agent observes the AT-1, which were the actions of the previous players. Now they are the observation of this new common agent. And the action of this common agent is the prescription functions gamma T. So gamma T1 and gamma T2 for the two players. So it puts a belief on the state of the system that it doesn't observe. So let's define a common belief pi t on xt. So this is again a vector xt1 to xtn. So this is the probability that xt is equal to xt given the observations of the common agent and actions of the common agent. So this is the common belief. And one can easily show that this common belief of the common agent can easily be updated using the Bayes rule. So pi t plus 1 can be updated using pi t, gamma t and at. So this new belief state is a function of previous belief state, previous action and previous observation. So it has this uncanny resemblance with the POMDPs. And where this update function f is independent of the policy of the common agent. And then we show that this pi t and gamma t is a control Markov process for this common agent problem, which basically implies that now there exist optimum actions of this common agent that are a function of pi t. So there exist optimum actions given by Markovian policies of the common agent. Gamma t and gamma 2t are a function of pi t through some Markovian strategy theta t, which equivalently means that there exist optimum policies of the players that depend on pi t and not on the whole action history. Furthermore, again using dynamic programming, I can find these optimum actions using for the common agent dynamic program, which goes as follows. At time t, gamma t star maximizes the instantaneous reward of the common agent and its expected future reward. And then I plug back in this gamma t star back in the equation to compute the reward to go at time t. So again, to summarize, I've introduced this notion of common agent and I've shown that this decentralized problem can be transformed into a centralized problem of the common agent, and I can use the usual machinery of the dynamic programming to compute the optimum policies of the common agent, which translates to the decentralized policies of the normal multiple agents.
So for every action history,
Yes.
there might be a separate pi t.
Right. So pi t is a function of for all
So
action.
you now lifted it to the space of continuum.
That's right. Exact same way you do it for POMDP. Okay. But the good thing here is that now I've come up with the strategies that depend on pi t, which is in a space that doesn't grow with time, and similarly for xit. Now I have a sufficient statistics that doesn't grow exponentially with time.
So for each history though, it's a different pi t. So it's
But I can update this pi t recursively.
Yeah, correct. But it will depend on the history.
Right. So
Pi
it's,
t plus 1 you're saying only depends on AT.
and pi t and at. So it's the exact same what you do in POMDP. Okay. All right. So this is what we know for the decentralized team problems.
And do they, excuse me, do they have some good algorithm to solve that? Because in POMDP you have this kind of nice hyperplan. And
That's a good question. I'm sure, so this is exactly POMDP, there's no difference, except for the fact that now you have actions which are gamma t, which are functions. So the space of optimization at each time t has increased from the action space to now a much bigger set.
No, let me correct you. You say it's POMDP, but it's exactly POMDP depending on the shape of f.
F is Bayes rule.
Okay.
So,
Okay. F is Bayes rule.
So it is POMDP, there's no difference. So whatever you have studied for POMDP, everything goes through.
And how you deal, and you have gamma t and at. Usually, I would say POMDP would be p of t and a of t, right? You will not have gamma t in POMDP.
So gamma t, in normal POMDPs, you don't have gamma t's because there's no decentralized information. Now here, think of gamma t's as the actions a's, and AT as the observations, in standard literature you call it Y's.
And how evolved A then? Okay, A evolved.
A is the evaluation in that individual.
Oh.
You can absorb it into the MDP,
Okay.
into the
Okay.
dynamics.
It's just like, okay.
Yeah, the action space is much bigger.
So conceptually, at least we have a framework to solve this problem. Okay. Now let's go to the games and let's see how is there a way for us to use these ideas in the games. So suppose I have a discrete time dynamical system with n strategic players over a time horizon t, and suppose player I have privately observed. So this is the same model. I don't think I should repeat that. Okay. So this model I've already talked about. Now the only difference is that from the teams, every player has a different objective. Alright. Okay. So this is a game problem. So again, the strategies, the equilibrium strategies are in the space of this much bigger set. But I want to restrict myself to the strategies that depend only on pi t and xit, because I believe that this is a sufficient statistics of the problem. So I want to find equilibrium strategies that only depend on this sufficient statistics. However, the unilateral deviations that I'm going to consider will be in the space of these general strategies. So these are not any bounded rational equilibrium, these are fully rational equilibrium. So again, remember that pi t was this belief on the private state of the users given the action history a1 to t minus 1 and gamma 1 to t minus 1. And this pi t could be updated using Bayes rule. Now for this particular information structure, what happens is that instead of putting this joint belief on all the xi's, I only need to deal with the marginals. And the joint belief is basically the product of the marginals because of the conditional independent structure that I assumed in the problem. So I only need to deal with this vector pi t, which is vector of the marginals, where this marginal is only a belief on xit, and these marginals can be easily updated using the Bayes rule as before. So this is one simplification that we have in the problem because of the conditional independent structure. Now, based on this framework, we present a two-step algorithm to find perfect Bayesian equilibrium of the considered game. And we call these perfect Bayesian equilibrium as structural perfect Bayesian equilibrium because they depend on this history only through these sufficient statistics. So in some sense, they're Markovian. And this algorithm consists of two parts. In a backward recursive part, I'm going to construct an equilibrium generating function theta, which you can think of as a policy of the common agent. And in a forward recursive way, I'm going to generate my strategies beta star and mu star from theta, which I'll show you is a perfect Bayesian equilibrium. So this is the backward recursion, which is like the main meat of the algorithm, and this is how it goes. So you define an equilibrium generating function theta t and a set of functions vit as follows. For all pi t plus 1 for all common beliefs and for all xi t plus 1, you first define this reward to go of player I as 0 in a similar way you do it for dynamic programming. Now in a backward recursive way for time t, t minus 1 and so on, for every belief vector pi t, you generate gamma tilde t, which is generated by operating theta t on this pi t vector, where this gamma tilde t is a solution of this fixed point equation. So I'll just talk about this fixed point equation a little bit more. So I have this gamma tilde t is a solution for every pi t. So for every pi t, I have a solution gamma I t that maximizes a reward to go function for player I. So this is current reward and future reward. This gamma I t is maximized over gamma I t, which puts a measure on AIT. So AIT is here and here. But gamma IT also appears in the update of the belief. I don't maximize on the gamma IT that appears on the belief. I use the same solution that appears, that is the solution of this problem. So I construct a new fixed point equation where the solution of the problem is both on the left hand side and the right hand side. The solution updates the belief of the common belief, but I only maximize over on the measure of player I's actions. Okay?
So I didn't follow. So you're saying that it's not an iterative procedure?
It need not be. I'm not sure it's it's not a contractive fixed point.
So what is the what is the conceptual difficulty?
I'll tell you. So let me go back to the team and see what we were doing before. So this was a dynamic program for the team. My optimum action gamma t star was maximizing over gamma t, and gamma t was putting a measure on AT given xt, and gamma t was also coming in the update of pi t. So the gamma t had two roles to play. In this case, I have gamma it of xit. I'm maximizing only over the measure I'm putting on AIT, which is here and here. But in order to update the belief, I'm using the same solution that I'm seeking here. So this is gamma tilde, this is gamma tilde. I'm only maximizing over gamma it. And I'm fixing gamma t minus I. So I'm fixing the gamma ti for all the other players. I'm maximizing over only my current player i's actions, keeping the gamma tilde t here as a solution which updates the pi t.
So are you thinking of breaking that as gamma tilde ti and gamma tilde t minus I and optimizing only over I?
Right. So here this is a solution for every xit, and for all players I'm going to generate gamma tildes. There's a whole list of gamma tilde for all the players, for all the xi's, that solve this big fixed point equation. Okay. Any questions on this fixed point equation?
How do you find gamma?
So this gamma tilde is a solution of this fixed point equation.
And is there a way of doing it? A smart way of solving it?
So okay, let me rephrase the question. Do we have an existence proof first of all, whether there exists a solution of this fixed point equation? For dynamic games of zero-sum games of incomplete information, we know that VIT is continuous, and you can use the standard Brouwer's theorem to prove, or Kakutani's fixed point theorem to prove that there exists a solution, although that is a non-contractive fixed point equation, so you may not have an algorithm to converge to one of these. In general, this is an open question whether there exists a solution for this fixed point equation. So far, all the problems that we have seen that there does exist a solution. Like numerically, we have seen the solution, but we don't have a proof.
That means that when you study, my question is more that when you program that on computer, it's kind of brute force where you try.
It's an iterative way. So we start with the policy iteration kind of way. We start with some VT. We start with some gamma t. We maximize and we put it back, and then
And you hope that at some point
it converges. Yeah. Okay. But we don't have a proof. Okay. Any questions? Okay. So again, like we find the solution of this fixed point equation, we put it back in, and we compute the reward to go at time t for player I. So we do this backward recursively. We generate for every pi t, we generate theta t of pi t as gamma tilde t using this process. This generates this function theta. And now in a forward recursive way, I generate equilibrium strategy and beliefs of the players as follows. At time t is equal to 1, the common belief is basically product of the priors given to me, and this is like obvious, you can't escape it. Now, in a forward recursive way, going down in the game, for every history, I define my strategies beta star I as theta it operated on pi t, where pi t is my equilibrium belief. And then I update my pi t, the equilibrium belief, using the base rule, and this theta t, which is the equilibrium strategies. So I go down in the game. I start with my initial priors of the game as the equilibrium belief. My belief, and at every time t, my strategies are basically evaluating this theta t on the equilibrium beliefs. And my equilibrium beliefs and next time is the base rule using the previous belief and the strategy that I just computed. Any questions? So this is very straightforward. We show that this is actually so this beta star and mu star that we just computed is a perfect Bayesian equilibrium of the game, which means that for every time t, for every history of the game of player I, this is its expected reward from time t to capital T, and this is when all the players play equilibrium strategies at the equilibrium belief. And this perfect Bayesian equilibrium means that the reward that you will get by playing these strategies at these equilibrium beliefs, the user I does not want to unilaterally deviate, which means that if user I, the reward that it will get at this equilibrium beliefs and strategies is always greater than equal to the reward it will get if all the other players play equilibrium strategies at the equilibrium beliefs, but only user I unilaterally deviates. So this is, we show that this is indeed a perfect Bayesian equilibrium for this game. So this kind of concludes how can we find a perfect Bayesian equilibrium for the game I considered so in this model. Any questions here? No? Okay. So I want to say that this was the work done in 2015 where we started with this model of conditionally independent types of the players, and there was a similar paper by Ouyang and their co-authors where they assume the same model but they have a different technique to compute such equilibria. Since then there has been a lot of work to extend such models. So in 2016 we extended this model when the players don't observe their types perfectly but they make some noisy observation YIT. So you can think of this as a POMDP version of the MDP. So instead of observing your types perfectly, you are now making a noisy observation. We also specialize this to linear quadratic Gaussian games where the update is linear, causes are quadratic, or the costs are quadratic and the random variables are Gaussian, and we have some more results when does the solution exist. In 2018, all these models were extended to the model where suppose there is one single state of the system xt which evolves as a control Markov process, and there are users which observes YIT which is conditionally independent across players conditioned on the state xt. And this model basically subsumes all these models. There's another model where we assume that instead of the conditionally independent types of the players, we assume the types of the players to be arbitrarily correlated across the players. So there's some prior Q such that all the types of the players are arbitrarily correlated. This again a similar methodology goes through, but I feel this is kind of like the bottleneck of this whole methodology. I conjecture that one cannot find a sequential decomposition for the games when the types are arbitrarily correlated and they're also dynamically evolving. And the reason is not because of the fixed point equation, but of the fact that there does not exist a sufficient statistics. That you cannot break this higher order beliefs on the other players. So in these kind of games, what happens is that every user has to put a belief on other person's private information, what they think about your private information, what they think about what you think about their private information, and so on. And these higher order beliefs can be summarized into this common belief and the current private information in these problems. But for this problem, I don't think that is possible, and that is probably the only reason you cannot solve such games in general. So this is like the state of the art for these particular games. I want to just mention one more thing before concluding the talk, that this is not just for this particular game, but this is like a new idea in these games, or idea of coming up with a new fixed point equation that goes through in many different games. And I want to just briefly mention there's another class of game called mean field games, where there are multiple players, infinite number of players. So the n number of players go to infinity, and they are homogeneous selfish players. Each player observes a private type XIT, which is finitely valued. And they also observe a mean field population state, which means that how many players have type in different states. So it's like a population mean field of everybody. So they don't observe everyone's type, but only a distribution of their types. And so again, this is, sorry.
Yeah. No, but please finish and then I will ask the question.
So there's again asymmetry of information in the sense that every player only observes XIT privately and publicly ZT. And they take the action, which is a function of xi1 to t and z1 to t. Player i's type evolves as a control Markov process that only depends on his previous type, action, and the mean field state. And each player gets a reward as a function of its own type, action, and the mean field state. And every player wants to maximize its total expected reward. And here I'm considering a finite horizon problem with a discount factor delta. So this is a model for the mean field game. Here you can show that the mean field state evolves through this equation, which is called McKean-Wilsov equation for the discrete time. So the zt plus 1 can be written as a function of zt and gamma t. And there's a corresponding fixed point equation which solves this problem, where now I maximize gamma tilde t. I maximize over the action ai for gamma, but I put the same update in the mean field gamma tilde t as the solution itself. So it has a very similar structure as we had in the previous problem. Instead of the base rule, now I have a McKean-Wilsov equation for the update of the mean field. So the same idea goes through in these mean field games, and it also decomposes this class of games. Any questions? Yes.
I think I have three questions.
Yes.
And perhaps I miss it, but why? So I understand that for completeness, you want to assume that you have all history and all the actions.
Yes.
When you take your decision.
Right.
But assuming that you don't take that, does it not simplify the whole analysis?
It doesn't. So if you don't have perfect recall, I am not sure if
Markovian, just you take Markovian policy.
So are you asking a question, does there exist an equilibrium in Markov policy?
No. I'm asking whether or not your methodology cannot be applied for just Markovian policy.
But we are giving the policies that I have are Markovian, right?
Okay.
What I'm generating are Markovian, even though their unilateral deviations are in general policies.
So then the second question is, I don't remember for imperfect information game, but I know there is a Folk theorem in dynamic game saying
For perfect information there is.
for perfect information, and then you know that you can always achieve the global optimum.
Pareto optimum.
And can you do that?
That's a very good question. I think that's a question that could be explored using this. I haven't seen anything on that.
So I don't know. And are you aware of any Folk theorem already on Bayesian Nash equilibrium?
I am aware of some Folk theorems on incomplete information games. They use a different kind of machinery to solve this, but I think this is a promising approach.
Oh, okay. Okay.
All right.
And if you take, so I think you take everything in finite horizon, right?
You can extend it to infinite horizon.
Yeah. So the thing is, we know that with discount problem within finite horizon, you have a fixed point that converge. So this, did you check whether or not can help you to prove the convergence to your fixed point in this case? Or
Again, the fixed point is not, so first of all, there doesn't exist a solution for incomplete information games. And all the existence proofs in such kind of games are non-contractive using Kakutanis. So I don't know of any algorithm that will provably converge to the equilibrium. Okay. All right. So I want to conclude this talk with a simple example. Like we have developed this whole huge machinery, and I want to see what do we get out of this. So this is a public goods game that I took from this book by Freudenberg and Tirol. It's a classic game theory book in economics. So the game is as follows. So the public goods game, if you don't know, these are games where it could be relevant to cyber physical system security, but these are games that have been studied in the economics literature. For example, if you want to propose a bus service in the system, in a city, or open a park. So when you want to do one of these public goods services, you can get money from anybody, but everybody will enjoy the service irrespective of whether you paid for it or not. For example, if you get a bus service, you have the option of enjoying the bus service whether you pay the taxes for it or not. So you have the option of free riding on the other person who actually paid for the system. So in this simple example, suppose there are two players and they have the option either to contribute towards a public goods, let's suppose a park, or not contribute, like which I represent by action 1 and action 0. And each player has a type, which is her cost of contributing. It could be low, which means that they are probably rich, so they don't have a lot of cost to contribute. Or the cost of contributing could be high, which means that they're poor. And these xi's are static and they're IID across players with some known probability Q of it being high. And each player contributes. If any of the player contributes, the public good is produced and the utility one is enjoyed by both the players. And this is the game matrix of the players. So if player 1 contributes and player 2 contributes, both of them get utility 1, but they also pay some amount of contributing, which is their private information, which is x1 and x2. Similarly, if none of them contribute, nobody gets anything, nobody pays anything. And if only one player contributes, that both of them get utility 1, but only one player pays the cost. So there's a possibility for the other user to free ride on the other user. Okay, and we are looking at the infinite horizon repeated game. So the strategies of the player depend on their static type xi and action history of all the players at time t. So we analyze this infinite horizon repeated public goods game using our methodology, and these are the strategies that we found for these games. So these are the probability. So on this axis, this is the probability of any player to contribute. So these are symmetric strategies for both the players. This is the probability that they will contribute. This is when delta discount factor is 0.5. So if the cost of contributing is low, there's a much larger region on which the player is willing to contribute. And if the cost of contribution is high, there's a much smaller region on which the player is willing to contribute. Okay. Now, very surprising thing happens when I increase the discount factor delta. So if I increase from 0.5 to 0.95, my willingness to contribute when my type is low, when my cost of contributing is low, shrinks down. So I'm less willing to contribute here. But when my cost of contribution is high, now I'm more willing to contribute when I increase my delta. Okay. And I want to ask you this question, anybody, like how can you explain this? Is there an intuitive way to think about it? That why any player would be less willing to contribute as I increase the delta when my cost of contribution is low, and more willing to contribute when my type is high? Is the question clear?
In the interest of time, maybe you can
Alright.
the answer.
So, in the single agent problem, there are two effects of the action. One is estimation and control. That's a classic control problem. But in these multi-agent problems, there's a new dimension of the action, which is called signaling, which means that my action can reveal part of my private information. Now, as I increase my delta, which means as my future becomes more important, I don't want to reveal my private information to the other person, because if the other person knows that my type is low, that person will ask to free ride on me. So in order to avoid myself from being free ridden, I'm willing to take the hit in the current time. So I'm willing to, I maintain some sort of ambiguity about my private type with respect to my actions by playing this strategy, so that now if I play action 1, it's not clear if my type was high or low. So the other person cannot deduce my private information from my action and cannot hurt me in the future. And that's why we see this kind of behavior, which is like you're deceiving the other person from your action so that they don't learn about your private type. Okay, so this is something new that we can observe from these methodologies that was not possible before. I would like to conclude by saying that this is like a new idea in these games that we have come up. So we come up with an algorithm to compute perfect Bayesian equilibria, and similar ideas goes through for mean field and stochastic Stackelberg games. There are a lot of interesting questions that one can think of. For example, proving the existence of the fixed point equation, or studying very specific kind of games and finding structural properties, or even doing dynamic mechanism design for these kind of games. So basically, this is like giving you a new tool. What dynamic programming has done for dynamic optimization problem, this new tool can do it for the dynamic games of incomplete information. And with that, I would like to conclude, and I'm happy to take any questions.
Let's thank Deepanshu.